A cosmic library holds stories written by colliding galaxies. These titanic clashes are not mere accidents, but authors scripting the universe's grandest tales of creation and destruction. By the end of this journey, you will understand how these violent events forge the very elements of life and dictate the ultimate fate of our own Milky Way. We will uncover why a serene spiral galaxy can be scrambled into an elliptical giant, and what happens when supermassive black holes awaken from their slumber. How does the story of our own cosmic home make you reconsider your place in the universe? Our universe is far from empty space dotted with lonely stars. It is a bustling metropolis of matter, a grand cosmic web where galaxies gather into vast clusters and superclusters, all strung together along invisible filaments of dark matter. Think of it not as a dark void, but as a sprawling, three-dimensional city map, with gravity serving as both the architect and the city planner. This immense structure is the true stage for the epic dramas of colliding galaxies. Our own home, the Milky Way, is not a solitary wanderer. It is part of a modest neighborhood known as the Local Group, which includes the great Andromeda galaxy and dozens of smaller dwarf galaxies, all bound together in a gentle gravitational embrace. But this embrace is not static. It is a slow, relentless dance choreographed over billions of years. Within even larger galaxy clusters containing thousands of members, this dance becomes exponentially more complex and crowded. Gravity is the patient force that sets everything in motion. It tugs persistently at every galaxy, pulling them from their random trajectories and onto converging paths. A near miss can warp a galaxy's spiral arms, while a direct hit is a foregone conclusion written in the laws of physics. This immense backdrop of structure and force is what makes a galactic collision not a random accident, but an inevitable event, a destined meeting between cosmic titans. This first contact between galaxies is a spectacle of cosmic grace. Two immense spirals, each home to hundreds of billions of stars, do not simply crash. They begin a slow, gravitational tango that unfolds over hundreds of millions of years. Their initial approach is a delicate ballet, where the invisible hand of gravity reaches out first. As they draw nearer, these tidal forces start to warp the very fabric of the galaxies. Imagine the gentle but persistent pull of the moon on our oceans, but amplified to a scale so vast it can bend the shape of an entire island universe. The beautiful, symmetric spiral arms are the first to succumb. They are not ripped apart but gently pulled like cosmic taffy into long, streaming tails of gas, dust, and stars. These magnificent arcs, often stretching for hundreds of thousands of light years, are the most visible signature of a galactic dance in progress. Yet this beautiful distortion is far more than a destructive force. It is a powerful catalyst for creation. As the galaxies swing past each other, their immense gravitational fields violently compress the vast clouds of hydrogen gas that drift between the stars. This compression is like a shock wave, triggering a chain reaction. Dense pockets within these clouds collapse under their own gravity, heating up until nuclear fusion ignites in their cores. The result is a firestorm of starbirth. Entire clusters of brilliant new stars flare to life, illuminating the drawn-out tidal tails with a blue-white glow. These stellar nurseries are far more intense than the quiet, steady star formation happening in an isolated spiral like our own. This is starburst activity, a ferocious and dazzling burst of creation born directly from the chaos of the encounter. So the dance, for all its apparent violence, does not merely destroy, It clears the slate and forges new material, setting the stage for everything that follows. It proves that in the grand narrative of the cosmos, an ending is often just a dramatic and spectacular beginning in disguise. This ferocious burst of creation, known as a starburst, is the universe's most spectacular fireworks display. It is a direct and violent consequence of the galactic dance, a period where star formation explodes from a gentle simmer into an uncontrollable inferno. The physics behind this is both simple and profound. When two galaxies intermingle, their colossal clouds of interstellar gas do not pass through one another peacefully. Instead, they slam into each other like titanic weather fronts. This violent collision creates immense shock waves that race through the gas, squeezing it with pressures far beyond anything found in an isolated galaxy. Think of it like crumpling a piece of paper in your hands. The empty spaces are compressed into a dense, tight wad. On a galactic scale, this compression triggers the ultimate chain reaction. Countless pockets of gas and dust are forced over a critical threshold, their own gravity causing them to collapse in on themselves. As each cloud core collapses, it heats up dramatically until the temperature and pressure at its heart become so extreme that nuclear fusion ignites. A new star is born. In a starburst galaxy, this process does not happen to one cloud at a time. It happens to millions simultaneously, lighting up the galactic landscape with the brilliant, blue-white blaze of stellar youth. We can witness this incredible process firsthand by looking at the Antennae Galaxies, a pair of spirals caught in a spectacular cosmic merger. From our vantage point, they appear as a tangled, luminous wreck with long, streaming tails that give them their name. But within that chaos lies a stellar nursery of unbelievable productivity. The Antennae Galaxies are forming new stars at a rate hundreds of times greater than our own quiet Milky Way. Vast, glowing pockets of hydrogen gas compressed by the collision are furiously giving birth to superstar clusters, each containing millions of infant suns. This is not the slow, steady pace of normal cosmic evolution. It is a frantic, almost desperate burst of creation, as if the galaxies are using their final moments of individual identity to forge as many new stars as possible. This narrative flips our intuition about cosmic violence on its head. Destruction and creation are not opposites here, they are two sides of the same coin. The same colossal forces that tear galactic structures apart are also the primary engine for stellar birth, seeding the universe with new solar systems and potentially new cradles for life itself. But this ferocious starburst is only one act in the larger drama. At the very heart of each colliding galaxy, a sleeping giant begins to stir. Most large galaxies, including our own Milky Way, harbor a supermassive black hole at their center, a gravitational behemoth with a mass millions or even billions of times that of our Sun. In a quiet, isolated galaxy, this monster often lies dormant, a silent king on a dark throne. But during a galactic collision, everything changes. The same gravitational dance that pulls on spiral arms and compresses gas clouds also funnels a colossal feast of material directly toward these central black holes. Vast rivers of gas and entire star clusters are dragged inward, swirling into a vast, glowing disk of superheated matter called an accretion disk. As this material spirals toward the event horizon, it is compressed and heated to temperatures of millions of degrees, causing it to blaze with unimaginable energy. The dormant black hole awakens, transforming into what astronomers call an active galactic nucleus. This is one of the most powerful phenomena in the universe. In its most extreme form, this active nucleus can become a quasar, a beacon so luminous it can outshine every star in its host galaxy combined. visible clear across the cosmos. In slightly quieter manifestations, we see Seyfert galaxies, where the brilliant core shines through the galaxy's own structure. This transformation turns the black hole from a passive occupant into the galaxy's dominant power source, a hidden puppeteer suddenly pulling the strings of energy and matter on an epic scale. The eventual fate of these two awakened giants is a cosmic subplot written in gravity itself. As the galaxies complete their merger, the two supermassive black holes, now both active and consuming, begin their own final dance. They spiral toward each other, trapped in a binary embrace, and will ultimately collide in an event that will shake the very fabric of space-time, sending out ripples known as gravitational waves. This final merger does more than create a single, even larger black hole. It unleashes a tremendous kick of energy that can sterilize the galactic core of gas, effectively shutting down future star formation in the central regions and permanently altering the galaxy's structure. The awakening and eventual merger of these central black holes is therefore not a side effect of the collision. It is a core narrative thread that dictates the final energy output and evolutionary path of the entire newly formed galaxy. This final merger of two spiral galaxies does not produce a larger spiral. Instead, it forges something entirely new and structurally ancient, an elliptical galaxy. This morphological metamorphosis is one of the universe's most profound rewrites. The graceful, rotating disk of a spiral, with its defined arms and bustling star-forming regions, is fundamentally scrambled into a smooth, featureless swarm of stars. How does such an ordered system lose all its structure? The answer lies in the chaotic physics of the collision itself. During the long dance, a process called dynamical friction acts as a cosmic brake. As stars and dark matter from one galaxy gravitationally interact with those of the other, they transfer orbital energy, slowly dragging the two galaxies closer. This friction erases the clean, circular orbits that characterized the original disks. Then comes the final act, a phenomenon known as violent relaxation. When the two galactic cores fully merge, the combined gravitational field undergoes a massive, rapid shift. It is like suddenly shaking a container full of marbles. The stars, now subjected to this wildly fluctuating gravity, are thrown onto random, chaotic orbits in every direction. There is no preferred plane of rotation left. The result is a three-dimensional puffball of stars, an elliptical galaxy, where the stellar population ages collectively with little new star formation. We can witness this predicted transformation not in real time, but through the power of supercomputer simulations. These digital models allow us to fast-forward billions of years, watching as two beautiful spirals swing past each other, their arms pulled into streams, their cores circling, and finally, their structures dissolving into a single, glowing ellipsoid of ancient suns. This narrative forces us to see every galaxy not as a permanent island universe, but as a single frame in a long cosmic film, its form dictated by its violent and collaborative past. So the serene, reddish glow of a distant elliptical galaxy is not a sign of a quiet life, but the final, calm signature of a colossal merger, a story of two spirals that collided and wrote a new ending together. The serene galaxy we see today is often a carefully preserved crime scene. Its current structure hides a turbulent history of ancient collisions, events so far in the past that their light faded eons ago. But astronomers have learned to become cosmic detectives, reading a fossil record written in the motions and compositions of stars themselves. This stellar archaeology allows us to uncover the assembly history of galaxies, proving that even the most tranquil spiral, including our own Milky Way, is built from the remnants of violent mergers. The evidence is not in glowing gas clouds or brilliant starbursts, but in the subtle, ghostly trails left behind. Look at a long exposure image of a galaxy, and you might see faint ribbons of stars arcing around it, structures known as stellar streams. These are the shredded remains of smaller dwarf galaxies that ventured too close, their stars pulled into long, looping orbits that trace the path of their destruction like cosmic breadcrumbs. One of the most dramatic examples is right here in our galactic backyard. Data from the Gaier Space Telescope revealed a colossal structure woven through the heart of the Milky Way, nicknamed the Gaier Sausage. This is not a single stream but a vast population of stars moving on highly eccentric radial orbits, plunging directly toward the galactic center and back out again. Their unique motion is a dead giveaway. It is the unmistakable signature of a dwarf galaxy, perhaps as massive as 10 billion suns, that smashed directly into the young Milky Way around 10 billion years ago. That colossal impact fundamentally scrambled our galaxy's early structure, puffing up its central bulge and contributing a huge fraction of the stars we see there today. Beyond their strange paths, stars also carry a chemical fingerprint of their origin. Stars born together in the same gas cloud share a specific chemical composition, a unique tag that persists for billions of years. When astronomers find large groups of stars within our galaxy that possess a distinct chemical signature, different from the native Milky Way population, it points to an external origin. These are the surviving populations of ancient, assimilated galaxies, their unique DNA preserved in their light. By mapping these stellar immigrants, we can piece together a timeline of galactic cannibalism. Our Milky Way was not born in its current majestic form. It was built over cosmic time by consuming dozens of smaller neighbors, each merger leaving its own faint scar in the stellar population. What does this mean for our sense of cosmic home? We are not living in a pristine, isolated island universe. The very stars in our sky are a mosaic of galactic wreckage, a permanent monument to the violent and collaborative process that built everything we see. The quiet spiral we call home is, in truth, a living museum of its own dramatic past. These ghostly stellar streams are not the only evidence of an invisible hand at work. The most profound narrative written by colliding galaxies is one we cannot see at all, a detective story that points to the very fabric of the cosmos. The plot revolves around a cosmic crime scene known as the Bullet Cluster, two galaxy clusters that have smashed through one another in one of the most energetic events since the Big Bang. The visible evidence is spectacular, with hot gas detected in X-rays piled up between the two clusters like a colossal cosmic train wreck. But the true mystery lies not in what we can see, but in what we cannot. Using a phenomenon called gravitational lensing, astronomers can map the cluster's total mass. Gravity bends the fabric of space-time, acting like a lens that distorts the light from galaxies far behind the cluster. By measuring this distortion, scientists can effectively weigh the cluster, creating a map of its total gravitational pull. When they did this for the Bullet Cluster, they made a startling discovery. The map revealed that the bulk of the mass was not where the visible gas was. It was in two separate, ghostly clumps, each centered on the groups of galaxies themselves. This was the smoking gun. The collision had literally pulled the clusters apart, but in a way no one expected. The clouds of hot gas made of normal matter interacted strongly during the collision, slamming into each other and slowing down. But the mysterious dark matter, which does not interact with light or with itself, passed right through the carnage unscathed, carrying the majority of the mass with it. This cosmic accident provided one of the most direct proofs that dark matter is real. It is not a modification of gravity. It is a substance, an invisible scaffolding that holds the universe together. The story of the Bullet Cluster forces us to rewrite our understanding of galactic narratives. The beautiful dance of colliding galaxies, the starbursts, the black hole awakenings, all of it is just the visible surface of a deeper drama. These events are fundamentally orchestrated by dark matter, the unseen author whose gravitational pen scripts the fate of everything we see. So when we look up at a serene spiral or a featureless elliptical, we are not just seeing a collection of stars. We are looking at the shadow cast by an invisible giant, a permanent reminder that the universe is dominated by a mystery we are only beginning to comprehend. The violent splendor of colliding galaxies paints a picture of cosmic chaos, yet the reality is almost eerily quiet. If you could stand on a planet during such an event, the most terrifying aspect would not be the sound of crashing stars, but the profound, unnerving silence. A common fear is that galactic mergers are like cosmic car crashes, with stars exploding in fiery head-on collisions. The truth is far stranger and hinges on a single, staggering fact: the overwhelming emptiness of space itself. The average distance between stars in a galaxy is so immense that if our sun were the size of a marble, the nearest star would be another marble thousands of miles away. Now picture two entire galaxies, each with that same incredible void passing through one another. The stars themselves are like ghostly travelers, slipping past each other unnoticed in the dark. The real collision does not happen between the stars, but between the thin, diffuse material that fills the space between them, the interstellar medium. This gas and dust is the true actor in the drama. When two galaxies meet, their interstellar media slam together like invisible weather fronts, creating the shockwaves that trigger the starbursts we see from afar. A perfect analogy is two immense swarms of bees flying through each other. The individual bees, like the stars, almost never touch, but the air disturbed by their wings, the collective force of their passage, interacts violently. It is this gravitational turbulence, this disturbance in the invisible fields, that writes the true narrative. The galaxies are not destroyed by material impact. They are reshaped by an unseen hand, their stories rewritten by the gentle, relentless pull of gravity over hundreds of millions of years. This silent, gravitational storytelling is the true force that forges new galaxies from the old, proving that the universe's most epic tales are written not in fire and impact, but in the quiet, patient language of spacetime itself. The silent storytelling of gravity reveals a cosmic hierarchy of violence, while the epic merger of two spiral galaxies is a dramatic, transformative event. It is not the most common narrative. Far more frequent is a quieter, more insidious form of galactic interaction, a slow-motion consumption known as galactic cannibalism. In this tale, the universe operates on a simple principle: the big eat the small. Our own Milky Way is a prime example, not a solitary giant but a gravitational predator surrounded by a retinue of smaller dwarf galaxies. These tiny satellites, like the large and small Magellanic Clouds visible from the southern hemisphere, are caught in our galaxy's immense gravitational well. Over billions of years, they are slowly being digested. The process is subtle, a gentle gravitational tugging that pulls streams of stars from the dwarf galaxy, weaving them into a faint, luminous halo around the Milky Way. This is a minor merger, and its effects are cumulative and long-term. It does not destroy the large galaxy's spiral structure. Instead, it gently thickens its disk, like adding layers to a cosmic pastry, and can spark modest, localized waves of new star formation. It is the primary way large galaxies grow, through the steady, silent accretion of smaller neighbors. But contrast this with a major merger, the clash of titans we explored earlier. This is not a quiet meal. It is a catastrophic collision between two galaxies of roughly similar size. the dynamics are entirely different, a battle of near equals where neither gravity well can dominate the other without a fundamental restructuring of both systems. The outcome is not a thickened spiral, but the complete annihilation of the original disk structures and the birth of an elliptical galaxy. The difference lies in the sheer amount of gravitational energy involved. A major merger injects so much chaotic motion into the stellar orbits that the organized rotation of a spiral disk is impossible to maintain. The system is violently shaken into a random, three-dimensional swarm. Think of the difference between a large fish slowly nibbling plankton from the water and two massive whales breaching and crashing together in a monumental struggle. One is a method of steady sustenance, the other is a world-altering event that churns the entire sea. This hierarchy of cosmic interactions paints a picture of galactic life cycles. A galaxy like our Milky Way grows steadily through countless minor mergers, its spiral beauty preserved even as it consumes its smaller companions, but its long-term fate is already written. In about 4.5 billion years, we are set for our own major merger with the Andromeda galaxy, a truly epoch-defining clash that will scramble both our spirals into a new, giant elliptical galaxy, a completely new type of cosmic island. This narrative shows us that galaxies are not static monuments. They are dynamic beings growing through silent cannibalism until they finally meet a partner that forces them to evolve into something entirely new, their stories forever entwined in the final product. The silent stories of galactic cannibalism and epic mergers are not confined to the galaxies themselves. Their narratives spill out, painting onto a far larger and almost invisible canvas, the intergalactic medium. We often think of the space between galaxies as a perfect, empty void, but it is not. It is filled with an incredibly thin, superheated gas, a sea of primordial matter that has existed since the dawn of time. This intergalactic medium, or IGM, is the universe's ultimate background, and colliding galaxies are the artists that violently reshape it. When two galaxies collide, the resulting shockwaves do not just ripple through their own gas. They blast powerful winds of material out into the cosmic void, slamming into the thin intergalactic gas. This process, known as shock heating, supercharges the IGM, raising its temperature to millions of degrees. It is like throwing a red-hot ingot into a placid lake. The water sizzles and steams as the energy dissipates. This galactic pollution does not stop with raw energy. The same starbursts that create millions of new stars also produce countless supernovae. These stellar explosions are cosmic forges, creating heavy elements like iron, oxygen, and carbon, and then blasting them out into space. Colliding galaxies act as immense pumps, ejecting these newly forged elements from their stellar nurseries and seeding the intergalactic medium with the very building blocks of planets and life. This process, called metal enrichment, transforms the pristine primordial gas into a more complex chemical soup, forever altering the potential of future galaxies that will form from this enriched material. The collision's impact is also written in ghostly structures that can persist for hundreds of millions of years. As supermassive black holes awaken and launch powerful jets of relativistic particles, these jets can plow through the intergalactic medium for vast distances. They inflate colossal, invisible bubbles of magnetic energy that can only be seen with radio telescopes. These are radio lobes, immense structures that often dwarf the galaxy that created them, standing as long-lasting monuments to a past eruption. In some extreme cases, the gravitational turmoil of a collision can be so violent that it completely strips a galaxy of its gas. This stolen material is then stretched into vast, hot halos that glow faintly in X-ray light, marking the grave of a galaxy's future star-forming potential. So the next time you see an image of two galaxies merging, Look beyond the tangled stars and brilliant starbursts. See them as fountains, spraying enriched material and colossal energy into the cosmos, painting their story onto the universe itself and setting the stage for the next chapter of cosmic evolution. This brilliant flash from a quasar is not a gentle light. It is a cosmic firestorm, a beacon so intense it can outshine every star in its host galaxy combined. The ignition of these extraordinary objects is one of the most direct and dramatic narratives written by colliding galaxies. Think back to the galactic dance, where gravity funnels vast rivers of gas inward toward the central black hole. For a quasar to flare to life, a supermassive black hole requires a feast of epic proportions, a continuous and massive inflow of fuel. An isolated, quiet spiral galaxy simply cannot provide this. Its gas is too settled, too peacefully orbiting in the disk. A major galactic collision is the ultimate caterer for this cosmic banquet. The violent gravitational turmoil of the merger violently shakes the entire galaxy, destabilizing the orbits of billions of gas clouds and flinging them directly toward the center. This creates a raging, superheated whirlpool of matter around the black hole, an accretion disk that glows with the raw energy of infall. The transformation is staggering. A previously dark and dormant object with a mass of millions of suns suddenly becomes the dominant energy source for an entire galaxy, shining with the power of 1 trillion stars. We see these quasars often in the early universe, a time when galaxies were close together and collisions were far more frequent. They are the brilliant signatures of cosmic adolescence, a period of intense growth and violent activity. But the quasar's story does not end with its brilliant flash. This outpouring of energy is so immense that it actively writes the next chapter of the galaxy's life. The radiation and heat from the quasar's accretion disk drive powerful winds of superheated gas, blasting outward at a significant fraction of the speed of light. These are not gentle breezes, they are galactic-scale hurricanes that sweep through the galaxy, violently pushing against the very gas clouds that are the raw material for new stars. This process, known as feedback, is a cosmic form of self-regulation. The quasar, born from the gas-rich chaos of a merger, now uses its incredible power to clear the galactic core of that same gas. It effectively shuts down the starburst that its own birth required. This feedback narrative dictates the ultimate size of the galaxy and the future of its central black hole. By expelling the fuel for both star formation and its own meal, the quasar ensures that the galaxy will not grow indefinitely. It places a limit on its own growth and orchestrates the galaxy's transition from a chaotic, gas-rich youth into a stable, gas-poor maturity. The local event of a black hole being fed thus echoes across the entire galactic structure, a perfect example of how the hidden narratives of colliding galaxies can shape cosmic evolution on the grandest of scales. These galactic crucibles are where the universe learns chemistry. The violent starbursts ignited by a collision do more than just light up the cosmos. They become factories for the very elements that compose our world. This process, called nucleosynthesis, is the universe's method of cosmic alchemy, and it operates at a scale we can barely fathom. Inside the heart of every massive new star born in a starburst, a relentless nuclear fire rages. For millions of years, these stars fuse hydrogen into helium, but that is only the beginning. As a star ages and its core grows hotter and denser, it begins to forge heavier elements step by step. Helium atoms are fused into carbon, carbon into oxygen, and so on, building a layered onion-like structure with iron accumulating at the very center. This is the endpoint of stellar fusion. Creating any element heavier than iron actually consumes energy instead of releasing it. So how do we get the silicon for rocks, the gold for jewelry, or the uranium for nuclear power? The answer lies in the spectacular death of these very stars. When a massive star can no longer support its own weight, its iron core collapses catastrophically in a matter of seconds, resulting in a supernova explosion. This final, violent act is the ultimate cosmic forge. The unimaginable energy of a supernova blast provides the extreme conditions necessary to create every element in the periodic table heavier than iron. In that fleeting, brilliant flash, a single star seeds its surroundings with a rich inventory of newly forged elements, from the calcium in your bones to the silver in a photograph. Now follow the journey of one atom born from this chaos. A silicon atom is forged in the heart of a supernova during the peak of a galactic starburst. The titanic explosion hurls it outward at nearly the speed of light, mixing it with the expanding shell of stellar debris. For millions of years, this atom drifts through the turbulent interstellar medium of the merging galaxy, a single speck in a vast cloud of enriched gas. Eventually, the gravitational pull of a dense, cold pocket within that cloud draws it in. This pocket, now laced with heavy elements from countless supernovae, begins to collapse. It forms a new star, a second-generation sun, and around this infant star, a swirling disk of gas and dust coalesces. Within that disk, our silicon atom, along with atoms of oxygen, iron, and nickel, begins to stick to others, forming microscopic grains. These grains collide and clump together, growing into rocks, then asteroids, and finally, planets. That silicon atom becomes part of a grain of sand on a distant world, or perhaps the core of a rocky planet like Earth. This narrative connects us directly to the most violent events in the universe. The iron in your blood, the oxygen you breathe, every atom that makes up our planet and our bodies, was once created in the heart of a massive star that lived and died fast during a galactic collision billions of years ago. We are not merely observers of these cosmic stories. We are living testaments to them, made from the very ashes of stellar explosions that illuminated colliding galaxies long before our own sun was even a glimmer in the cosmos. Our own solar system, a tiny island of planets orbiting a single star, is not immune to the galactic narratives unfolding around it. When galaxies collide, the serene clockwork of planetary orbits is thrown into a cosmic roller coaster. The chances of our sun physically striking another star are astronomically small, but that is not where the true danger lies. The peril comes from the invisible hand of gravity, which becomes a chaotic and unpredictable force during a merger. As two galaxies intermingle, their combined gravitational field ripples and shifts. A planet like Earth, held in a stable, finely tuned orbit, can suddenly find itself in a cosmic tug of war. The gentle tugs from passing stars, once negligible, can now be amplified into a violent shove. A planet could be flung into a wildly elliptical path, bringing it scorchingly close to its star before hurling it back into a deep freeze. In the most extreme cases, a planet can be ejected entirely, thrown out of its solar system to become a rogue world, drifting forever in the cold, dark emptiness of intergalactic space. This is not a gentle reshuffling, it is a gravitational lottery with the highest of stakes. The most profound threat, however, may come from the frozen outskirts of a solar system. Every star like our Sun is thought to be surrounded by a vast spherical shell of icy debris called the Oort cloud. In a quiet galaxy, these comets and asteroids remain in a deep freeze, held in a stable, distant orbit. But during a galactic collision, the gravitational perturbations act like a cosmic pinball machine. A near miss by a passing star can send a gravitational shockwave through this cloud, dislodging countless icy bodies and sending them on a new, inward trajectory. A rain of comets begins to fall toward the inner solar system. For a planet like Earth, this is a potential extinction-level event. A single, large comet impact can throw enough debris into the atmosphere to blot out the sun for years, collapsing food chains and ending geological eras. This narrative forces a profound connection. The history of life on any world may not be a story isolated to its own planetary conditions. It could be a story written by the galactic environment. A period of great extinction on a distant exoplanet might not be due to its own volcanic activity or climate change, but a direct consequence of its host galaxy merging with another billions of years earlier. The rise and fall of alien civilizations could be dictated by the silent, gravitational tides of colliding giants, a cosmic connection spanning tens of thousands of light years. These magnetic fields are the universe's ghostly architects, tracing invisible blueprints across the chaos of a collision. While gravity provides the brute force of the narrative, magnetism provides the subtle, guiding hand. These fields are incredibly weak, millions of times less powerful than a common refrigerator magnet, yet they are woven through the vast expanses between the stars. In a quiet, isolated galaxy, they often lie dormant, flowing in orderly lines along the spiral arms. But when two galaxies collide, this invisible architecture is violently stirred into a frenzy. The same gravitational turmoil that pulls on stars and gas also stretches, amplifies, and tangles these magnetic fields. They are no longer gentle streams but chaotic whirlpools and powerful filaments, their energy dramatically increased by the motion of the collision. This tangled magnetic web then begins to write its own subplot into the galactic story. It influences the very flow of the gas, the lifeblood of star formation. The fields can act as a cosmic scaffold, providing support against the gravitational collapse of gas clouds, or they can channel material along specific paths, like invisible highways guiding traffic through a storm. This directly impacts how and where new stars are born, adding a layer of regulation to the ferocious starbursts. Without this magnetic influence, our computer simulations of galactic collisions would be incomplete, producing stars at the wrong times and in the wrong places. We cannot see these fields with optical telescopes, but we can listen to their story with radio ears. Radio telescopes are uniquely tuned to detect the faint synchrotron radiation emitted by electrons spiraling at near light speed along these magnetic field lines. By mapping this radiation, astronomers can trace the invisible architecture, revealing magnificent magnetic filaments stretching for tens of thousands of light years, often lining the spectacular tidal tails of merging galaxies. In systems like the Antennae Galaxies, these observations show magnetic fields powerfully amplified in the overlapping regions where the gas collision is most intense. This reveals a narrative of co-evolution, where gravity creates the initial drama, but magnetism steps in to direct the flow of energy and matter, shaping the final outcome of the entire system. To truly read the full story of a colliding galaxy, we must learn to see not just with light, but with the mind's eye, perceiving the silent, guiding force of these magnetic currents as they sculpt the universe from the shadows. At the very heart of a galactic collision, a final, spectacular consolidation takes place. The same gravitational currents that awaken black holes and trigger starbursts also act as cosmic conveyor belts, channeling entire star clusters and vast streams of gas on a direct course for the galactic core. This immense influx of material builds something extraordinary in the nucleus, a stellar metropolis of almost unimaginable density known as a nuclear star cluster. Picture a region of space that would comfortably fit within the distance from our Sun to its nearest stellar neighbors, but instead of a handful of stars, it is packed with millions. This is not a gentle grouping, it is a seething swarm where stars are separated by mere light weeks, their collective gravity creating a blazing, compact city of ancient suns. These nuclear star clusters are not born in isolation. They are the direct products of galactic cannibalism, built over billions of years as a large galaxy consumes its smaller dwarf companions. With each minor merger, the central star clusters of the devoured dwarfs are dragged inward and merged into the growing nucleus, a process of steady accumulation that writes a permanent record of past meals into the galaxy's very center. But sometimes the process of creation is so violent that it forges an entirely new class of cosmic object. Enter the mystery of the ultra-compact dwarf galaxies. Astronomers first noticed these strange entities hovering in the crowded fields of giant galaxy clusters. They appeared as faint, star-like points, but their light told a different story. They were far too bright to be single stars, and their spectra revealed they contained the mass of tens of millions of suns, all compressed into a sphere only about 200 light-years across. What were these cosmic chimeras, too small to be a true galaxy, yet far too massive and dense to be a simple star cluster? The leading theory paints a dramatic picture. An ultra-compact dwarf is likely the stripped and battered heart of a former galaxy. Imagine a small but normal dwarf galaxy orbiting a much larger one. Over eons, the immense tidal gravity of the giant predator galaxy pulls and shreds the dwarf, stripping away its outer layers of stars and dark matter. All that remains is its incredibly dense, resilient core, its nuclear star cluster, left orphaned and exposed. This stellar fossil, having survived the destruction of its host, now wanders the cluster as an ultra-compact dwarf, a ghost of a galaxy that once was. The properties of these objects are a direct archive of the violence that formed them. The age and chemical composition of the stars within a nuclear star cluster can tell us precisely when its host galaxy underwent its last major merger. An ultra-compact dwarf's immense mass and tiny size are a permanent scar, a testament to the gravitational forces that ripped its galactic home apart. They are the cosmic equivalents of archaeological relics, their very structure encoding a history of cannibalism and consolidation. This narrative forces us to look at the brilliant centers of galaxies in a new light. That dense, shining core is not a primordial feature. It is a trophy room built from the accumulated remains of countless smaller galaxies that ventured too close. The serene beauty of a galactic nucleus masks a violent and collaborative past, a story of construction written one devoured dwarf at a time. Our own galaxy is living on borrowed time. The grand narrative of cosmic collisions is not a distant spectacle but a future written in the motion of our nearest large neighbor, the Andromeda galaxy. Right now, it is hurtling toward us at a staggering 250,000 miles per hour, a closing speed that seems impossible until you realize the immense distance it has to cover. The first close pass will not happen for another 4.5 billion years. When that moment arrives, the night sky will begin a transformation more dramatic than any human civilization has ever witnessed. At first, Andromeda will simply grow larger, a faint smudge of light swelling into an unmistakable cosmic presence. As it draws nearer, its spiral structure will resolve with impossible clarity until it dominates the entire heavens. Then the true gravitational dance begins. The two galaxies will not hit head-on, but swing past each other in a gravitational slingshot, a move that will warp both of them beyond recognition. The serene disk of the Milky Way, the stable backdrop for all of human history, will be pulled and twisted. Its elegant spiral arms will be stretched into long, streaming tails of stars, gas, and dust, a brilliant but terrifying testament to the forces tearing our home apart. This first pass will be a spectacle of creation and destruction, triggering ferocious starbursts as gas clouds collide and light up the chaos with the blue-white fire of newborn stars. What would it be like to stand on Earth during this epoch? The sky would hold two colossal, intermingling galaxies, their cores glowing fiercely. The familiar band of the Milky Way would be gone, replaced by a tangled, brilliant web of stellar light. The chance of our solar system being thrown from its orbit is real, a gravitational lottery with the highest possible stakes. After this first dramatic encounter, the galaxies will swing apart, only to be pulled back together by their mutual gravity for a final, decisive merger. This second act will take another 2 billion years to complete. During this time, the two supermassive black holes at their respective centers will spiral toward each other, culminating in a collision that will shake the fabric of space-time with gravitational waves. The final product of this billion-year saga will be a completely new type of galaxy, an elliptical giant that astronomers have nicknamed Milkomda. All the structure we know will be erased. The beautiful star-forming disks of both the Milky Way and Andromeda will be scrambled into a smooth, featureless, three-dimensional swarm of stars. The night sky from a planet within Milkomda would be very different. It would be uniformly bright with no dark lanes of dust, and the sun would be just one of countless stars in a glowing, reddish-orange haze, the collective light of aging suns. This is not a speculative fantasy. It is the most robust prediction in all of galactic astronomy, backed by precise measurements from the Hubble Space Telescope that have tracked Andromeda's motion with certainty. The story of our galaxy, a tale that began with the assimilation of smaller dwarfs, will end with its own annihilation and rebirth into a new cosmic form. We are living in the gentle prologue of that story, a brief moment of spiral stability before the inevitable final chapter unfolds. This chaos of colliding giants does not merely destroy old structures. It provides the raw material for entirely new worlds to be born, stretching far from the central wreckage. In the magnificent tidal tales of gas and dust, gravity begins a new chapter. Within these long, streaming arcs, dense pockets of material can collapse under their own weight, igniting star formation and coalescing into small, independent galaxies. These are tidal dwarf galaxies, and they are cosmic phoenixes rising from the ashes of a galactic collision. Their origin story makes them fundamentally different from the primordial dwarf galaxies that have orbited larger galaxies since the dawn of time. Traditional dwarfs are dominated by dark matter, that mysterious, invisible substance that forms the gravitational backbone of the universe. But a tidal dwarf galaxy is born from the visible, ordinary matter that was flung out during the merger, the gas and dust from the galactic disks themselves. This means these newborn galaxies are made almost entirely of the stuff we can see and understand. They are, in effect, pure laboratories of baryonic matter, offering astronomers a rare chance to study how stars form and how galaxies behave without the complicating, dominant influence of dark matter. We can watch this process unfold in famous mergers like the Antennae Galaxies. Within their vast, sweeping tails, telescopes have identified several bright, condensed knots. These are not simply clusters of stars, they are nascent tidal dwarf galaxies in the act of formation, each one potentially becoming a new, small, and independent island universe. Their existence completes a profound cosmic cycle. The same immense gravitational forces that tear two large galaxies apart also gather the ejected debris and sculpt it into something new and alive with stellar youth. It is a narrative of rebirth written directly from the wreckage of conflict, proving that even in the universe's most violent moments, the seeds of new beginnings are always being sown. These galactic narratives are not just pieced together from ancient light. We can now witness their entire life cycle from beginning to end inside a machine. Supercomputers serve as our ultimate cosmic time machines, running vast numerical models that translate the fundamental laws of physics into a virtual universe. Scientists program the rules of gravity, the flow of gases, the formation of stars, and the feedback from supernova into lines of code. Then, they set two virtual spiral galaxies on a collision course and press play. The simulation does not run in real time, of course. It fast-forwards through hundreds of millions of years in a matter of days, allowing us to watch a process no human could ever live to see. We can observe in stunning detail how delicate spiral arms are drawn out into tidal tails, how compressed gas clouds ignite in waves of starbirth, and how supermassive black holes at the centers awaken and begin their final dance. This virtual laboratory is where theories are tested and our understanding is forged. Before we had these tools, the serene elliptical galaxy at the end of a merger was just a still image, a single frame from a long-lost movie. Now we can play the entire film. We can run the same collision over and over, tweaking the initial conditions slightly each time. What happens if the galaxies hit head-on versus a glancing blow? What role does dark matter play in holding the wreckage together? The simulations provide answers, showing us that the transformation into an elliptical is not just possible, but inevitable given the right conditions. They reveal how the chaotic process of violent relaxation randomizes stellar orbits, permanently erasing the ordered disk. These digital experiments are more than just pretty animations. They are rigorous tests of our deepest cosmological principles. When a simulation's prediction matches what we see in a real system like the Antennae Galaxies, it gives us profound confidence that we are correctly reading the hidden narrative. The computer becomes our translator, decoding the complex story of gravity, gas, and time that is written across the sky. This brilliant violence contains its own off switch. Galactic collisions are not runaway chains of creation, but self-regulating events with built-in feedback loops. The very forces that trigger furious star formation also work to shut it down, creating a delicate balance that prevents the universe from burning through its fuel supply in a single, brilliant flash. This negative feedback is the central plot twist in the narrative of a merger, ensuring a controlled and sustainable story. The first mechanism comes from the starburst itself. All those massive new stars live fast and die young, exploding as supernova within just a few million years. Each of these explosions is a titanic blast, and when they occur by the millions in a short period, their collective energy is staggering. This creates a galactic superwind, a hurricane of superheated gas that blows outward from the star-forming regions. This wind violently pushes against the surrounding clouds of cold hydrogen gas, the very raw material needed to make the next generation of stars. It can sweep this gas clean out of the galactic disk, effectively robbing the galaxy of its future star-forming potential and quenching the starburst it helped create. But an even more powerful regulator waits in the core. The awakened active galactic nucleus with its supermassive black hole unleashes a far more potent form of feedback. As the black hole voraciously consumes gas, it doesn't just radiate light. It can launch colossal jets of plasma and drive winds of ionized gas that move at a significant fraction of the speed of light. The energy pouring out from this tiny central engine can overwhelm the entire gravitational pull of the galaxy. These Aegean winds act like a cosmic fire hose, blasting through the galactic center and violently heating or ejecting the surrounding gas reservoirs. This process permanently shuts down the black hole's own food supply while also halting star formation across vast regions of the galaxy. We see evidence of this in many massive elliptical galaxies, which are often gas-poor and populated by old red stars. Their starburst days are long over, likely extinguished by the powerful feedback from a final, epic quasar phase. This self-regulation solves a cosmic mystery. Without these feedback loops, a major merger would consume all of its gas in one furious, short-lived burst, creating a single, immense wave of stars before sputtering out into a dark, dead galaxy. Instead, the interplay between creation and quenching stretches the narrative over a longer, more structured timeline. The feedback ensures that not all gas is used at once, that the central black hole does not grow uncontrollably, and that the final product is a stable, long-lasting elliptical galaxy. It is a story where the author, Gravity, also writes the final edit, preventing the tale from ending too soon. The violent history of our cosmos forces a difficult question about life itself. Does the chaos of colliding galaxies make life more likely, or does it snuff it out before it can even begin? The answer appears to be a paradox, a story of both existential threat and creative necessity. On one hand, the forces unleashed by a merger are apocalyptic for any fragile biosphere. The intense radiation from a newly awakened quasar at the galaxy's core can flood entire star systems with lethal X-rays and ultraviolet light, sterilizing planets from orbit and stripping away their atmospheres. Meanwhile, the gravitational chaos can disrupt the stable, circular orbits that allow for a steady, life-friendly climate, sending a once temperate world spiraling into its star or out into the frozen depths of interstellar space. Yet, these same cataclysmic events are also the very reason rocky planets like Earth exist at all. The heavy elements essential for a world of mountains and oceans, for the iron in your blood and the silicon in the ground, were forged in the hearts of massive stars born during ancient starbursts. Without the galactic collisions that triggered those furious waves of star formation and supernova, the universe would remain a primordial soup of hydrogen and helium, devoid of the complex chemistry that life requires. There is an even more speculative yet profound possibility. The same gravitational turmoil that flings stars from their orbits could also act as a cosmic disperser for life itself. The concept of panspermia suggests that microbial life, hardy enough to survive within asteroids or comets, could be ejected from one solar system and travel across interstellar space. During a galactic merger, the chances of such a life-bearing rock being captured by a passing star and seeding a new world increase dramatically. A collision could, in theory, mix the biological ingredients of an entire galaxy, spreading the spark of life from one star system to countless others. This duality reshapes our search for extraterrestrial life. We might instinctively look for quiet, stable spiral galaxies as the most likely cradles for complex civilizations. But perhaps the opposite is true. Perhaps it is the galaxies with a violent, stimulating past, those that have experienced the enriching fires of multiple mergers, that are the true galactic incubators, having been repeatedly seeded with the heavy elements and just maybe the biological precursors necessary for life to arise and evolve. The ultimate fate of life in the universe may not be written in the quiet corners, but in the brilliant, chaotic, and life-giving fires of cosmic collision. Even with all we have learned, the final pages of this cosmic story are still blank. The grand narrative of colliding galaxies is punctuated by profound mysteries that continue to challenge our understanding. One of the deepest puzzles revolves around the invisible architects of these events, the dark matter halos. We know these immense, ghostly spheres envelop every galaxy, but their exact properties, their shapes and density profiles, seem to dictate the ultimate fate of a merger in ways we do not fully comprehend. Why do some collisions produce majestic tidal tails while others result in a more chaotic scramble? The answer likely lies in the subtle details of these unseen halos, whose gravitational influence orchestrates the entire dance from the shadows. Then there is the enduring mystery of the galaxy morphology sequence. Why does the universe favor spirals and ellipticals? We know mergers transform one into the other, but the precise recipe that governs this transformation remains elusive. What specific combination of collision angle, gas content, and dark matter determines whether a serene spiral becomes a featureless elliptical or is somehow rebuilt into a new disk? This question strikes at the very heart of galactic evolution and identity. Further complicating the picture is the intricate physics of the gas itself. During a collision, we see gas clouds collapse to form stars, but the details are maddeningly complex. How exactly does turbulent gas cool and fragment? What are the precise triggers that initiate the collapse of a single dense core amidst the galactic chaos? Our current models still struggle to capture the fine details of this star-forging process. These are not mere academic curiosities. They are the keys to predicting the life cycle of any galaxy, including our own. Fortunately, we are on the verge of a new era of discovery. A powerful new generation of observatories is turning its gaze toward these cosmic puzzles. The James Webb Space Telescope, with its infrared eyes, can peer through the obscuring dust of merging galaxies to witness the birth of the very first star clusters in pristine detail. Meanwhile, the upcoming Square Kilometre Array, a vast radio telescope, will map the invisible hydrogen gas that fuels these collisions with unprecedented resolution, tracing the flows and shocks that our optical telescopes cannot see. Together, these instruments will read the hidden narratives of gas, gravity, and time with a clarity we have never before possessed. The story of colliding galaxies is far from complete. Every answered question simply reveals a deeper, more fascinating layer of mystery, ensuring that the next chapter of cosmic discovery will be the most thrilling yet. Every galactic collision writes its own unique story, dictated by its starting conditions. The narrative of a gas-rich spiral smashing into another gas-rich spiral is a dramatic epic of starbursts and transformation. These systems are brimming with the raw fuel for star formation, so when they merge, the resulting shockwaves ignite a firestorm of creation, often leading to a brilliant, blue-hued starburst galaxy and ultimately forging a new elliptical giant. But contrast that with the slow, quiet drama of two gas-poor ellipticals colliding. With little cool gas left to compress, there is no spectacular starburst. Instead, the merger is a dark, ghostly event, a silent pas de deux where the two swarms of aging stars simply pass through one another, their dark matter halos intertwining to create a larger, but equally quiescent, elliptical galaxy. The available fuel at the beginning entirely dictates whether the story will be one of brilliant, fiery creation or a somber, structural consolidation. The angle of impact is another author scripting the plot. A direct head-on collision is a brutal, fast-paced narrative. It drives a colossal surge of gas directly toward the galactic centers, rapidly feeding the central black holes and triggering an intense but potentially short-lived starburst. The resulting galaxy forms quickly, its structure scrambled by the violence of the encounter. A grazing encounter, however, is a more drawn-out saga. The galaxies make multiple close passes over billions of years, each swing pulling longer and longer tidal tails, gently funneling gas inward and prolonging the period of star formation. This creates a more extended and complex storyline, with the final merger happening only after a long, dramatic gravitational dance. The difference is like that between a sudden, devastating earthquake and the slow, relentless creep of tectonic plates. Even the cast of characters shapes the tale. A simple binary collision between two galaxies of similar size is a classic duel, a straightforward story of two titans clashing. But many collisions occur within crowded galaxy groups, leading to a complex, multi-generational saga. In a group merger, several galaxies can interact simultaneously, their gravitational influences pulling on each other in a chaotic ballet. This can lead to a series of minor mergers before the final consolidation, building up the central galaxy in stages and creating a rich history of stellar streams and multiple nuclei. The well-known Stephan's Quintet offers a stunning snapshot of such a multi-character drama, with several galaxies visibly influencing each other's destinies at once. The initial mass ratio is equally critical. When a large galaxy consumes a much smaller one, it's a tale of cannibalistic growth, a minor event that thickens the larger galaxy's disk but leaves its fundamental spiral structure intact. Yet when two behemoths of comparable mass meet, it is a true merger of equals, a catastrophic event that erases their past identities completely and forges an entirely new galactic entity. From the available fuel to the angle of attack and the number of participants, every initial condition is a narrative choice, writing a unique cosmic story into the fabric of the universe. The silent dance of colliding galaxies has echoed through human imagination for millennia, long before we understood their true nature. Ancient cultures looked to the starry expanse and saw not random points of light, but epic dramas, battles, and creation myths played out on a celestial stage. The Greeks told of the Titanomachy, a war among gods that shook the very heavens, a narrative that mirrors the violent restructuring of galaxies. Norse mythology described the wolf skull chasing the sun, a perpetual cosmic pursuit that resonates with the gravitational tango of two galaxies destined to merge. These stories were humanity's first attempt to explain the grand, often chaotic, movements they witnessed above, mapping their own fears, conflicts, and hopes onto the cosmos. This instinct to find narrative in the night sky is a profound part of who we are, a bridge between the objective universe and our subjective need for meaning. Modern science has given us the true script of these cosmic events, yet our artistic response has only intensified. Digital artists and data visualizers now use real astronomical data to create breathtaking visualizations of galactic collisions, transforming cold equations into swirling symphonies of light and color. These are not mere illustrations, they are translations, rendering the invisible forces of dark matter and gravity into a form our senses can comprehend and our emotions can feel. When you look upon a painting or a simulation of the Milky Way and Andromeda merging, you are not just observing a future astronomical prediction. You are witnessing a story of birth and rebirth, of an ending that is also a beginning, a theme that lies at the heart of so much human art and literature. This fusion of science and art deepens our connection to the universe in a unique way. Knowing that the iron in our blood was forged in the heart of a star born from a long-ago collision adds a layer of poetic truth to the scientific fact. It transforms the cold void of space into a place of shared history and shared substance. The cosmos becomes less an external object to be studied and more a participant in a continuous, collaborative story, one that we are only just beginning to read. Our science reveals the mechanics of the cosmic dance, but it is through art and story that we feel the music. Every thread we have followed, from starbursts to black hole awakenings, weaves together into one grand narrative. This is the story of a single, major galactic merger, a cosmic epic that unfolds over billions of years. It begins with the slow, gravitational approach of two spiral galaxies, their first delicate pass warping majestic arms into tidal streams. This initial act of distortion is also the first act of creation, as the violent compression of gas clouds ignites a firestorm of new stars, flooding the system with light and forging the heavy elements for future worlds. Simultaneously, this gravitational turmoil funnels rivers of gas toward the galactic cores, awakening the dormant supermassive black holes within. These monsters transform into brilliant quasars whose powerful winds begin to sweep the galaxy clean. The narrative then reaches its climax with the final merger of the galactic cores. This is the event of violent relaxation, where the orderly orbits of stars are randomized, scrambling the beautiful spiral disks into a smooth, three-dimensional swarm, an elliptical galaxy. The two central black holes spiral inward and collide, shaking spacetime with gravitational waves and releasing a final burst of energy that halts star formation in the core. What remains is a new equilibrium, a stable but gas-poor elliptical galaxy, its red-hued glow a testament to its aging stellar population. The enriched material blown out by supernova and quasar winds pollutes the intergalactic medium, seeding the void with the elements for future generations of stars and planets. This grand synthesis reveals that these are not separate stories. The starbursts fuel the black holes regulate the starbursts, and the resulting chemical enrichment changes the galaxy forever. This interconnected tale is not a rare catastrophe, but a fundamental driver of cosmic evolution, a repeating cycle of destruction and rebirth that has built the universe we see today. It is the hidden narrative behind the serene galaxies dotting the night sky, a reminder that every island universe has a dramatic past and a collaborative future written in the language of collision. These hidden narratives reveal a universe constantly rewriting itself, a cosmic dance where destruction and creation are inseparable partners. The violent chaos of a galactic collision is not an end, but a necessary phase of renewal, forging the heavy elements that become the building blocks of planets, oceans, and life itself. We are not mere spectators of this grand story. The iron in our blood and the calcium in our bones were forged in the hearts of stars born from these ancient, fiery encounters. Our very existence is a direct consequence of cosmic violence on an unimaginable scale, a permanent link between the biology of our world and the epic dramas of colliding giants. As our telescopes peer deeper and our simulations grow more sophisticated, we continue to unlock new chapters in this billion-year-old saga. Each discovery reminds us that we are part of a much larger, ever-evolving narrative, one written in the silent, gravitational language of the cosmos. We would love to hear your thoughts on these incredible cosmic tales in the comments below. If this journey through the mysteries of the universe captivated you, subscribe to join us as we explore even deeper.